So let's say we were asked to state the asymptotes of the following function. F at x is equal to x squared minus x minus 2 over x minus 2. And we would see that, well, the degree of the numerator, okay, is 1 degree higher than the denominator. So I know that it's going to have a slant asymptote. Right, that'd be your first thing. Second thing you would notice is that a value of 2 for the x would set the denominator for 0. So it has a vertical asymptote. Okay, and that's I'm just gonna write here at x equals 2. Okay, so what you would expect to see with this information is that you'd probably have a graph that, you know, looks something like this, let's say. Okay, and then, you know, a slant asymptote combined with a vertical asymptote, something like this. Now, the problem is, when you go to the actual graph, so the main question is then, how will we know if our function has a point of discontinuity or points? And simply put, I mean, you won't at first glance. What you should do is get in the habit of factoring the numerator and the denominator every single time in order to check. And so what I can do is I can give you this rule. Okay, that's going to make things easier. Once you factor your numerator and denominator, check for any terms that cancel out. Any term or terms that cancel out are points of discontinuity. At least it's the x values anyway. So I'm just going to write x values. And I graph y is equal to x squared minus x minus 2 over x minus 2. This is the graph I end up getting, which is a linear graph, which doesn't make a lot of sense. Now, if you go and you try this again, you'd still get the same results. The reason why for this is because sometimes rational functions have what we call points of discontinuity. So what points of discontinuity are coordinates that look like they're on the graph when we did all the, you know, traditional math in the algebra and gotten the asymptotes. But when we graph them, they aren't really there, like those asymptotes we just talked about, right? Or in some cases, intercepts. So the reason why this happens, why our, you could say, graphed function doesn't match the function that we've algebraically assessed, is that it probably got simplified from factoring and it removed those coordinates. So let me show you that that's the case with this equation here. So let's say I factor the numerator here traditionally. What I'm going to get here, okay, so you factor it using either the graph, you can graph it in isolation, or you could just factor it using decomposition, or you can use a quadratic formula. Either way is fine, you can get the same answer. This would break down into x minus 2 and x plus 1. And that's over x minus 2. And actually it should have been x minus 2, not x minus 1. That's just a miswrite here. Okay, so what I could see is that if I simplify this, the x minus 2's cancel out. And that leaves me with f at x is equal to x plus 1. So this really isn't a rational function after all. It's a linear function. And so there's a point of discontinuity at x minus 2. And removing that x minus 2 brought the function down a whole other degree. Now for the y value of this discontinuity, just simply plug in the x value, so this value, back into the original equation, and your output will be your y value of the point of discontinuity. The point of discontinuity is also called a hole in some cases. And so if we ask you for a hole or a point of discontinuity, we're really asking for the same thing. Now on a graph, you would write the point of discontinuity as a blank circle here. And if there was more than one, then you would put more than one blank circle along the line of the function, okay? And kind of like in our notations, right, your blank dot means a non-included value. So it's not really there, even though we can calculate it, it's an error, an extraneous error. So to determine the asymptotes, the x and y intercepts at the point of discontinuity for the following: x squared minus fx plus 6 over x minus 3. So what they're going to do is I'm actually going to save the asymptotes for the last, okay? And that's because if there is points of discontinuity and things factor out, if we take these asymptotes too early, we're going to basically describe points that are not actually there. So what we're going to do is let's factor this equation first. And so when I do that, I got x minus 3 times x minus 2. That's this factored version of the equation here, over x minus 3. And so, as I kind of predicted here, I have to factor those out, which means I know at the very least, okay, now write it down here, there's a point, so POD, a point of discontinuity, at x equals 3. Okay, because I had to cut out the x minus 3 factors here. Now, when I've simplified this, this is no longer a rational function in the sense of having a numerator and denominator. So I'm going to write no longer has a numerator over a denominator. So what that means is that there's going to be no horizontal asymptotes or vertical asymptotes. Okay, what I can do though is get the point of discontinuity. So now that I know that x at x equals 3, I have a point of discontinuity. Now I'll just solve for the y value, which I can go x minus 2.
I'm done with this.
So I just plug in the x coordinate into the final function here, and that gives me a value of 1. So then I know that, and I'll write it underneath here. I know that my point of discontinuity is therefore at 3 and 1. And this point would be a clear circle on the graph. So we're going to get our x and y intercepts finally by setting each side to 0. So we're going to go 0 for x-intercept is equal to x minus 2. And then, of course, doing the algebra, we get that x is equal to 2. And then, and remember, it's always going to be at 2 and 0. And then for the y-intercept, we're going to set the x to 0, like this. So then y is going to equal to negative 2, which of course will be written as 0 and negative 2. And so finally, we have all the properties of that function. Okay, now with this question, we're going to work backwards. We're giving you a graph, and this is a rational function. And from the graph we're giving, we're going to ask that you come up with the equation. So a couple of things here. I want you to see there's a clear dot here. That's a point of discontinuity. Okay, so I'm just going to write P of discontinuity. Okay, and that's at x plus 8. So what that means is that we know that x plus 8 must have been factored from the original equation. Now there's something else as well. We have an x-intercept here of x plus 4. Now that's important because from previous lessons, x-intercepts come from the numerator, whereas the vertical asymptotes come from the denominator. So we got x plus 4, and that's going to tell us something about the numerator. There's one other thing here. We see that there is a vertical asymptote at -2, right? I can see that the graph never approaches either of those. It seems to kind of stay away. So we're going to write here, vertical asymptote at x equals -2. So now with all the information we pointed out here graphically, we can kind of start to build the equation. So we know that it's going to be y is equal to something over another thing, or numerator over denominator, but we don't have an exact idea of what that is. So what we're going to do is, we know that there's an x-intercept at -4, and that the x-intercepts refer to the, or at least one of the factors in the numerator. So I'm going to write x plus 4 at the top bracket here. Now, to the point of discontinuity, if it's at x plus 8, then that means that it was something that got canceled from the top and the bottom. So I can put x plus 8 on both the numerator and the denominator. Now there's a vertical asymptote at x minus 2. And vertical asymptotes are the values which make the denominator equal 0. So that means I can also put x plus 2 in the denominator. Now, both these are going to end up in the second degree. What that second degree, or what the coefficient from the second degree is, we could probably figure that out later. But if they're the same degree, we know that they have a horizontal asymptote, which we should be able to match in the very end. But now, this gives us enough information to work backwards, FOIL the top and the bottom, and get our original rational expression. So that gives us the expression of y is equal to x squared plus 12x plus 32 over x squared plus 10x plus 16. Okay, so one last thing here that we can check. The degrees are both 1, and then when we want to find the horizontal asymptote value, we take the ratio of the leading coefficients between the numerator and the denominator. So if we go x squared divided by x squared, that equals 1, which means that right at a value of 1, right over here, we should see a line in which both of the sides of the graph approach but never actually reach. And we can see that with the red line here, that is true.